graph. Let us start our class today. Now, I have started this discussion of this problem, number 16, but we could not finish it. Let us finish go for the next problem before going for the next problem. Now, this figure shows the section of a beam. Determine the moment of resistance to bending in the bending in the y plane than in the x plane. If the maximum bend distance remains same in both the section. So what we are thinking here, first of all, we have to find out the moment of resistance to bending in y plane as well as the x plane, because we want to know the ratio between these two moment of resistance. And our assumption is the maximum bending stress remains same in both the cases. So we are having the same bending stress, and which is the maximum for both the cases. And moment of resistance, I've discussed it, I am writing again. It is the maximum moment which can be carried by the given section for a given maximum value of stress. It is not moment of resistance. It is the maximum bending moment. Maximum bending moment on a section for a given section for a given maximum value of bending stress. So we are saying that this section is supposed to have the maximum bending stress. So it is very clear from our definition of maximum bending stress is that it should have the maximum bending moment. Now, let us discuss what is this, what we have in this problem, what is the different dimension of the this section of this particular beam. So this is the cross section of the beam is given, whose what we have is the depth of this cross section, which is not shown here, that is equal to 150 millimeter. The latter part is given here. Unless you know it, you can't do any problem. This is the width, that is y, and there is a notch here or depression here and here. And the size of the knot is 25 millimeter here from the center to here, and 25 millimeter from center to here. And the size of these notches are 50, another side of the notches are 50 millimeter from this point to the upper plane, and 50 millimeter from this point to the upper plane. The notch size is same for both the notches. And we know that axis x-axis x plane is going through this line, and y plane is going through this line. So we have to, one main important thing here, you have to calculate the moment of inertia of the same section, either first for x-axis, then for y-axis. And we have to go, we know that bending stress is same, and so bending moment is maximum in both this section. So we have to calculate this ratio from both this side. We have to calculate the ratio accordingly. So what we have here, it is shown. What is have here? We have to find the ratio of maximum moment of resistance with X plane and do that in the Y plane, and you have to find the ratio. Now the section modulus in the X plane. Section modulus, you have to know the section modulus. We have to know the shear moment of inertia, and you have to know the distance of the maximum fiber from the section under consideration for which this moment of inertia is being measured. Now, first of all, let us go for the section modulus in X plane. So modulus of modulus of elasticity, modulus of inertia, moment of inertia, MOI is moment of inertia of the section XX. This is the section XX, and which will be equal to the moment of inertia of the complete section about XS, means full rectangular section. Moment of inertia you have to first calculate. Next, we have to omit or deduct the moment of inertia of 4 triangles about XX. What are the 4 triangles? This is one of the triangles from here to here. This is another triangle from here to here. This is one of the triangle from here to here, and this is another triangle from here to here. So its dimension is given. So we know the height of each triangle is 25, and the base of each triangle is also equal to 25. Because 75, what is this? This is given as 50, because this half of this height is total height is 150 of the rectangular section. So half will be 75 each, and we have given here that's from this point to this end point is equal to size is equal to 50. So from this point to this point, the size is also equal to 25, and both is the same. So size is 25 here as well as height is here. So base of this triangle is 25, and height of these triangles is also 25. They're both the same for all the triangles. So this is shown here, 25 to 25. So what we have to do, we know the moment of inertia of any triangle will be B into H, B multiplied by H to the power 3 divided by 12. If we are supposed to take the moment about any axis, any side of the triangle, where we are taking the x-axis or x plane as one of the side. So it will be 25 into the power multiplied by 20 power 3 power 3 divided by 12 multiplied by 4, as we are considering all 4 rectangles. So total so the moment of inertia of the total rectangle is 1 by 12 multiplied by base width is 100 and height is there, b is width is 100 and multiplied by 150. So 150 to the power 3. It is the bending moment of inertia of rectangle when we are considering the section about its central axis here, axis here. Just a second before. So this is the moment of inertia of the centroidal axis of the rectangle. That is moment of inertia of centroidal axis. This centroid passes through, the axis passes through the centroid. So about the axis, the moment of inertia will be 1 by 12, 100 into the power and pH cube. So we put the value of B and H as like this, and we also put the sides of the triangles like 25 into 25 to the power 3 multiplied by 4. So this moment of inertia will come out as 25.995 into 10 to the power 4 mm to the power 4. And the ZX means the moment of inertia divided by the distance of the maximum fiber, which is the half of the height of the rectangle, which is that is equal to 75. So if we put this I axis at 27.995 to the power 4, this is not 6 but 4. And divided by 75, it will become 0.373 into 10 to the power 6. It will be supposed to be 6. Now, section modulus in y plane. We are supposed to calculate what is the section modulus in along the y plane. Next, what is y plane? Y plane is given from this side to this side. This is the y plane. Thus, the section modulus of the rectangle of the component, that's also a central axis, but in normal to the x-axis. So my of the complete rectangle about y-axis, my of the two isolated triangles about yy. So why it is like this? Here we have two triangles here. Here, if one is here and another is here. Just 1 second. Now, so what we have here, we are supposed to find out the moment of inertia about this axis y, about the plane yy of this rectangle of the given dimension and this rectangle. They both are same, and both the dimensions are also same. So first of all, we have to know this is the rectangle drawn in separate, and base of the rectangle is 50 and height of the rectangle is 25. And if we draw a straight line about this CG of this rectangle, it will go through like this, and which is equal to 25 by 3 from this base and 25 plus this is the distance 25 and 50 25, because this was from here to here height is 25, and from here to here the length is 50, half of this length 100. So this here to here it is 50. So the distance should be distance from the y-axis, y plane will be 25 plus 2 into 25 by 3. So this angle, this line passes through the CG of this triangle, and this CG, this line has the distance 25 by 3 from this base and 2 into 25 by 3 from the apex. So as we are considering the distance from y-axis to y dash here, so we have to add 25 plus 2 into 25 by 3 to know the distance of this rectangle. To know the distance of CG of one of the isosceles triangles, means it has of same side of two sides. So the yy of the triangle, we know about the distance is b into h to the power 3 divided by 36, and the y of the triangle, about this is about y dash, and that is b into h to the power 3 divided by 36, and yi of the triangle is of about the yi axis is the moment of inertia, same moment of inertia plus the area of the triangle, half base into altitude plus multiplied area of the triangles, means 50 is the base, 25 is the altitude, divided by 2 multiplied by the distance from the square of the distance from the axis of moment of inertia under consideration, which is 25 plus 50 by 3, which is given here. This distance is, we have just discussed, this is given here. So if we simplify and solve, then this is the moment of inertia of the rectangle with base is equal to 150 now, and height is equal to 100. So 1 by 12 divided by 150 multiplied by 100 to the power 3 minus 2 into 50 into 25 to the power 3 divided by 36 into 50 into 25 by 2 into 50 plus 30 divided by 3, which we have to put here, and just we have we have calculated the moment of inertia about y axis. So after simplification, I yx is becomes 10 into 10 to the power 10.286 into 10 to the power 6. So that Zx, the moment of resistance, is given as the section modulus about xx is given as, or ratio of the moment of resistance is given as maximum distance. Moment of inertia with the maximum distance of the maximum area fiber, that is 50. So if you take the ratio, it will be like this. So what we want to now calculate the moment of the ratio of the moment of this resistance, which z y or z xx, both we are, and the ratio becomes 0.552. Okay, this problem is finished now. Let us go for the next problem. Now, here, what we found here shows the section of a beam. What is visible here? This section of a beam. Determine, the figure shows the section of a beam. Determine the ratio of its moment of resistance to bending in the YY plane to that in the plane XX if the maximum bending stress remains the same in the two cases. This problem is set. Here we also given X section of the beam whose dimensions are told, and we have to find out the ratio of the moment of resistance to about the YI axis and about XX axis. Now, this ratio of the moment of resistance to bending in y plane to that of x plane, we have to suppose to find out. So we have to find out first the section modulus in x plane. The modulus of moment of inertia MY of the complete rectangle about xx minus MY of the two semicircle about xx. So what is the this is the complete rectangle with base equal to 100, with height equal to, it is also given as 150, not written here, 150 millimeter. Same. And this is the moment of inertia one cycle here and moment of inertia one cycle here. But this is a semicircle of 25 millimeter diameter and same here on the right side. So the moment of inertia this two, each multiplied by 2 will be omitted from the moment of inertia of the foot section, a moment of inertia of the foot section, and this equation will be like this: Ixx, the 1 by 12, 100 is the base, height is 150, 150 to the power 3 minus 2, and the moment of inertia of a total cycle is equal to pi by 64 d to the power diameter d to the power 4. That is, half of them will be because you have to take half of them because it is the semicircle here. So half multiplied by 2 again. So it becomes remains same, pi by 4, 90 to the power 4. This becomes 24.9 into the power 6. This is for full rectangle. This is for two semicircles. So Zx, the distance of the maximum fiber of which has the maximum distance from the x-axis, means from here to here. This edge of this fiber has the maximum distance, means half of this length, that is divided by, that is 150 by 2 equal to 75. So moment of inertia divided by 75 is equal to section modulus 0.332 multiplied by 10 to the power 6 millimeter. It is the section modulus about x-axis. Now we are supposed to calculate the section modulus about y axis. Now, section modulus about y plane. These are all the dimensions are shown here. And next important thing is the distance Now y plane is here from here, and we are supposed to find out the distance of the center of cavity of this semicircular plane from y axis. And if we draw a line through this CG, and this line is supposed to be y dash y dash. So first we have to find out the moment of inertia of this semicircle about y dash, about this y dash axis. Plus, then we have to add this area of this circle from multiplied by the square of the distance from between y to y dash axis. So the first moment of inertia of each semicircle about y-axis will be 1 by 12. Then let I is the moment of inertia of each semicircle about y dash y dash. So I y dash is first of all 1 by 12, 150 to 10 to the power 150 to 10 to the power 100 to the power 3, which means this is the moment of inertia of the full rectangle with the central axis equal to y. So that will be the base will be 150 and height will be 100. So 150 half 12 1 by 12 by this is 1 by 12 multiplied by 150 to base, that is multiplied by 100, that is into height 1 to the power 3 is the moment of inertia of the rectangle about y-axis. Next, minus I, the moment of inertia of each semicircle, it should be multiplied by 2 because we have 2 semicircles, and we have to find out the moment of inertia of each of them about y-axis. So we put this equation like this: 12.5 to the power 6 minus 2 into I. Now y dash I dash just have told you the neutral axis of the each semicircle. So area of such each neutral axis pi by 4 d square, that is 45 is the radius, so 90 is the diameter, pi by 4 d square, and half is the area of each of them. So area of each of them, because it's a semicircle, not a circle, so the area of each semicircle becomes 3181 millimeter square. A is the distance of the centroid from the center, that is 4 into r divided by 3 into pi. That is, r is the radius divided by 3 into pi. Distance of this centroid of the semicircle from the center is 19.1 millimeter. So what I've shown, this is the centroid. This is a straight line, y dash is drawn through the centroid of this semicircle. The centroid of the semicircle is away from the center of this semicircle is by angle equal to A, which is given by 4/3 y dash. It is 19.1 millimeter. So you have to find out the distance of this circle from the y dash axis, y axis. So my of each semicircle about y axis will be moment of inertia of each semicircle about its own neutral axis, plus area into b square. So moment of inertia of each semicircle about the AB minus area into a square plus area into b square. About AB, area multiplied by a square. This is AB. This is, so you have to find out the moment of inertia of each circle about it. And about it then, and as we want to know the moment of inertia about y-axis, so you have to omit the moment of inertia of this semicircle multiplied by the distance from y dash axis to AB. Thus, it has become pi by 64 to the power 90 to the power 4 into half, because it is a semicircle, minus area 3181 multiplied by A, that is a square, that is 19.1, which is given here. We have calculated here 19.1 plus the area 3181 multiplied by the distance of the straight line y dash from y axis, that is 50 minus 19.1, because from AB to y dash y is distance is equal to 50. So if you omit 19.1 from the 50, we'll get the distance B, or distance from y dash to y axis. So if you put all the numerical values here and solve, and we get the moment of inertia of each semicircle about y-axis is equal to 3.487 into 10 to the power 6 20 or cube. So y-axis, moment of inertia of the full section, rectangular section with semicircular group will be equal to 12.5 into 10 to the power 6 minus 2 into 3.45, 3.487 into 10 to the power 6, which we are putting here, and we got the calculation as equal to IYY is equal to 5.526 per 10 to the power 6 millimeter square 4. So ZYY, the section modulus about the y-axis, is the moment of inertia about the y-axis divided by the distance of the maximum fiber of the section, which is equal to 50, half of the distance, half of the width, height B here is equal to 100 by 2 is equal to 50. So ZYY is equal to 0.1105 into 10 to the power 6. The moment of resistance, so the ratio of the moment of resistance, MYY or MXX, is we put both this value of ZYY and ZXS as equal to 0.1105 into the power 6 divided by 0.332 into the power 6 equal to 0.333. That is the ratio we want to calculate. Next problem 13. Let us hope that I can finish. Next, the tension flange of a cast iron, the tension flange of a cast iron I section beam is 250 millimeter wide and 50 millimeter deep. The compression flange is 100 millimeter and 50 millimeter deep, whereas the wave is 300 millimeter and 300 millimeter. Find the load per meter run which can be carried over a 4 meter span of a simply saturated beam, simply supported beam. If the maximum permissible stress is given as 90 MPa in compression and 24 MPa in tension. So what we first understand what is the tension flange, what is compression flange, and what is wave. Both because dimension of tension, compression, and wave is given. So what is given? This is the I section of the beam. What is given? Tension flange is here 24 millimeter wide, 50 millimeter deep. So here it is shown the bottommost flanges of the I section is 24 millimeter width and with depth 50 millimeter. This is our tension flange. Why it is given that if the constant beam member is loaded like this, there is a beam member here and beam member here. If it is loaded by a load here, it will bend like this, and bottommost portion of the beam, bottommost fiber of the beam will be tension with under maximum tension, and topmost fiber of the beam will be under maximum compression. So as per our problem, the side of the tension size of the tension beam is 240 multiplied by 50, and size of the compression beam, which is the topmost section, which is topmost flange, which is 100 millimeter divided by multiplied by 20, and the width is given as 30 millimeter width and of length 300 millimeter. So we can divide this total I beam by an area of 240 multiplied by 50 millimeter, 300 multiplied by 30 millimeter, and 100 multiplied by 20 millimeter. From the center, from the end of the AB side to the center is 200 millimeter, and that from the topmost, from the CG of the topmost flange is given by 360 millimeter. This is given, and that the dimension of the from here to here, from dimension of the wave is given as 300 millimeter, and dimension of the top flange is in height of the top flange is 220 millimeter. These are all dimensions are given. So what we are supposed to do? First of all, we have to find out the moment of the area. The area is 120. That is, the area is here. This is 100. This is 100 multiplied by 20. This is one of the area here. 30 multiplied by 300, which is given here. 30 multiplied by 300, 100 by 20, 30 multiplied by 300. Another is 250 multiplied by 50. 250 multiplied by 50. That is the maximum tension flank. That is the side of the area of the maximum tension flank. So if we make the calculation here, we'll have the area is 23,000 mm square. So what will be what is y? That is the distance of the fiber from area. So first of all, we have to find out the a divided by area divided by y. So we have to find out the individual area. Area multiple. So we have to do. We know the area multiplied by area. Moment of inertia is equal to area multiplied by the square of the distance, y square. So in order to know the y, we have to find out the distance, the area into the maximum area in the distance from the y itself. So first of all, find out what is 2000 here. This is the area here, 2020 multiplied by 100. This is the total area, that is 2000, 22 multiplied by 2000, and its distance from the y-axis is given as, its central distance from the y-axis given as 360 millimeter. So its distance from this axis here, let me discuss another thing. Now find what we are supposed to do is the load per meter run, means the distributed load, in such a distributed load, which can be carried out over a 4 meter span by a single supported beam. If the 4 meter span means the length of the beam is around 4 meters, and the maximum permissible tension and compression is given as 90 for compression and 44 for compression. So first we have to find out the load. So you have to find out the moment of inertia about the surface about AB. So in order to find out the moment of inertia, this is the surface AB. We have to find out the moment of inertia about this surface because we are this beam is simply supported and it is bent like this. So its moment of inertia is supposed to be taken about this axis which over which it is being bent. So first of all, we have to find out the value of y, about the full value of y. Find out the value of y. So one is the area multiplied by 360, the distance from the axis AB, which is 300 plus this is given as 360 millimeter. This is 200 plus 360 millimeter. Next, we have to find this area, which is 300 into 300, 300 into 30, which is given here. 300 into 30 means 9,000, and its central axis given is here 200 millimeter. This area into here, area into y. This is also another area into y, and another is 12,000 into 25, which is the area here 2,400 multiplied by 50. That is 12,000. 12,000, and its distance of its CG will be half of 50. That is 25. So 12,025 divided by the full area. So here area multiplied the distance of y is given as 122.6 millimeter. So the central axis distance of the central axis from AB is given by this particular formula here. Next, we have to find out the moment of inertia about AB. That is 1/3 into 10, 1/3 multiplied by the distance 250 minus 30, that is the two area, into 50 to the power 3, that is 250 multiplied by 30 means this area. We are just omitting this portion because we have to take into account differently. So this is the length multiplied by the half of the height. Half of the height is given as 250 into 250 minus 30 into height, that is 50 to the power 3 into 1/3, plus the section for section B here. This is the section. And next for 300 multiplied by 30 to the power 3. 30 into 300 plus 50. That is 300. We have taken from the base, so it is 300 plus 50. And this is from here, 30. So that is 1/3. And 12, we are going to 100 into 20 to the power 3. It is 100 into 10 to the 20 to the power 3. Plus 200 into total area multiplied by the area of the figure, that is 2000 multiplied by 360 to the power square. That is 2000 multiplied by 360 square. For Q plus R, for P plus V plus R, that is P plus V plus R, and R is this plus its distance is that is 350, 370 to 10, 360. Yes, 360 is the distance multiplied by 360 square into 2000. This is the area 22,000. So distance of this particular area itself. Area multiplied by the distance from the AP, that is the square of the triangle. So we have to take a point of view of this triangle, rectangle, this rectangle, as well as its distance from the rectangle himself. We are doing the same because we have to take in the full rectangle here, and here we are taking both these two rectangles here, and here we are taking the distance of this rectangle here. So the IAB will be 696.77 into the power 6 to the power 4. So IXX, next, IXX, the moment of inertia of the section AB multiplied by the area, multiplied by area into the distance from XX to AB. That is, we have calculated 122.6 to the power square multiplied by area. Area we also calculated for the full area. So you put all these values, so you get the final moment of inertia. About IXS is 351.06 into 10 to the power 6 millimeter to the power 4. Now, the stress, we know the maximum allowable stress in tension as well as maximum. So the stress in tension reaches its maximum value. Sigma C divided by 24 is a distance of IC, 350 minus 120 divided by IC. Now sigma C is equal to 48.46. So if we take the ratio of which is within the safe limits, the moment of resistance will be sigma divided by y into I. This I is calculated, sigma is calculated.
Hello, sir. Hello. सर एग्जाम ऑनलाइन होगा कि ऑफलाइन होगा सर?
ऑनलाइन
होगा ना सर?
हाँ ऑनलाइन হবে।
Okay.
Online হবে। I will display the question like this. Okay.
अच्छा जी सर।
You have to answer and you have to upload your answer in Google Classroom. I understand that number again.
ठीक है सर।
Upload individual number within that time. After that, it cannot be uploaded. Okay. Now, which is within the set limits. The moment now the stress in the tension is the maximum. First, we have to understand that sigma C, sigma T. What is sigma C? And sigma T is given as sigma maximum permissible stress in tension is 25 MP, 24 MP. So thus we put maximum tension here, and the stress is maximum to flow the maximum compressive stress, that is YC, distance of 370, total distance, that is 300 plus 50 plus 20, that is total distance 370, and this distance from the x-axis from Y is given here. We have just calculated 124, that is the distance of Y. So distance from X is given, the difference between this Y